Hi, everybody. Well, thank you very much for joining us today for Bringing the Human into Your Process Planning, which is the fifth and final webinar of our Next Step webinar series 2021. My name is Philip Glennie, and I'm very proud to be joined here today by Karen Banar, Technical Solutions Consultant at Siemens Digital Industries Software, and Allison Stevens, Professor and Program Coordinator at the Advanced Ergonomic Studies Program at Fanshawe College. I do want to take a moment to note here that as part of her teaching work, Allison is always training and graduating the next generation of ergonomists who are ready to use the tools you're going to see here today to perform the kinds of value-added ergonomic analysis and consulting that we're going to be looking at. So I just want to give a quick shout out to the great things Allison is doing at Fanshawe. And if you're ever looking to work with or hire the next generation of top talent in ergonomics, she's a great person to connect with and speak to, and we'd be happy to help you connect with her if you'd like to. We're very grateful to have both Allison and Karen joining us here today. So here's a quick agenda for today's webinar. I'm going to walk through a quick introduction, then we're going to move to Karen and the power of virtual human modeling, and then Allison will speak about the use of digital models in manufacturing, followed by a quick Q&A. So here's a quick introduction into digital twinning solutions. But before that, I just want to say a little bit about us at Long-Term Technology Services. Our mission at LTS is to be your trusted partner for exploring new digital solutions that are going to make your organization more efficient and impactful. And we're trying to fulfill that mission at two levels. First, we're looking at your long-term success by helping you build a common digital thread through a number of industry solutions that span from your product design and engineering, your production scheduling, your plant management, and even your ergonomic practices, which is what we're going to be looking at today. But it's also our mission to meet companies where they are. In other words, if there's anything you see in this webinar that seems like it's maybe too much of an upfront investment or time, or you need too much internal expertise to really get the most out of it, please just know that at LTS, it's our responsibility to create situations that work for you. We need to offer clear proof of concept on these types of solutions, as well as very strong ROI with a very compressed payback schedule. And we do that through a combination of software, training, and consulting that's tailored to your exact needs. We're also very proud to be a Siemens Smart Partner and Technology Partner, and we specialize in working with and helping small to medium-sized businesses. So here are a couple key trends just to help contextualize what we're about to see here. As many of you know, there's a number of trends that are forcing companies to become leaner, smarter, and more agile while somehow increasing the quality of their products and production. And some of these trends are what you see listed here, like consumer-driven customization, smart machines, hyper-automation, global competition. Customers want things more personalized, flexible, faster, with better quality. And we believe that the holistic digital twin is the way to meet these trends and their accompanying demands. So you might have heard the expression digital twin before. So what do we really mean by this? Well, if you think of traditional simulation, you're usually thinking of a geometric or kinematic model that's pretty hypothetical. It's not the reality, in other words. But a digital twin is really a virtual replica of your product machine, or as we'll find out here, human being, that goes much deeper into different realms, especially when it comes to orthopedics and ergonomics with the human model that we're talking about here. On the machine side, you can get into the level of electrical, mechatronic, thermal transfer, pretty much any sort of real-world effects you can name it, you can simulate those. So now you're talking about a type of simulation that truly offers a stand-in for a real device, object, or person that can also be connected to them in real time. In the case of machines, that would be sensors in many cases, and with the human, we're going to look at this today, but that would be motion capture technology. And that has big implications for the way we do things in manufacturing. And while this is all good for machines, today we're talking about extending this approach to the human body and ergonomic analysis. And so how do you really capture all of that complexity of a flesh and blood human being? I mean, how do you really model that at the level you would need to replicate or even surpass the value of doing those simulations with a real person? And today, that's really what this webinar is going to help you answer. It's this approach that allows you to take the performance of individual tasks and use reliable human models to standardize and scale those practices throughout your organization. So keep in mind that while creating human simulations might seem like a lot of work at times, you can compare that to the savings and improvements you'll make by using those simulations to standardize the performance of tasks. And so once you've decided to work with a digital twin technology, it then becomes a question of scope. And if you've attended any of our previous webinars, any of the previous 4, you'll have seen that digital twin technology runs all the way from plant-level simulation down to the level of the production line, robotic work cells, or robot station. And for this webinar, we're focusing on a very special area, which is the level of the human body. But it does use many of the same digital twinning principles that we apply to these other layers. And with that, I would like to turn things over now to Karen Banar of Siemens Digital Industry Software to share her screen and offer her next segment of the presentation. Karen?
All right, can everybody hear me okay?
I can.
Perfect. So today we're going to talk about Process Simulate Human. The Process Simulate Human tool resides on top of this software called Process Simulate. And the purpose of this software is really to simulate and analyze your manufacturing processes. And it's modular, so you can kind of add on what you need. We're obviously going to focus on the human module today, but we also have an assembly module that can help you with your virtual builds. So it's basically just looking at, we like to call it parts flying through space. So it's looking at the order of operations and whether or not it is feasible from a clearance standpoint. And then we also have the robotics module. We have virtual commissioning, which allows you to validate some of your PLC logic before you go into production. And then we also have a discrete event simulation tool, plant simulation, that looks at more of a line or plant level. And it looks at things like, are there bottlenecks in certain stations? It looks at throughput, station utilization, whereas Process Simulate is more of the kind of the individual workstation level. And we're going to look at that now with the human. So the Process Simulate Human tool includes this 3D digital human. It allows you to populate your designs or work areas with this digital human to assess your product, your processes, or your facility, the layout. It allows you to virtually explore the advantages or maybe disadvantages of either different designs or different layouts within a work cell without the need for an actual physical prototype. So this can all be done up front virtually. We can simulate different loading conditions as well, like whether they're lifting, pushing, or pulling. So we can look at the force and the direction of the force, and then analyze the injury risk to the human. And then once a simulation is built, you also get a timing report that will give you an estimate for each task and the overall cycle time as well. So in some of the movie files that you'll see a little later in this presentation, you'll see our older mannequins. In these slides here, though, you're going to see our latest generation of mannequins. We have spent several years working on these new figures. Two key changes are they're totally textured from head to toe, making them look very visually very realistic. And the anthropometric scaling has also been revised. So one limitation in the past was you didn't have as much control of the individual body areas and their size. So now we have kind of detailed control over the individual body scaling, like the chest and waist circumference, the different breadths. So we can really represent realistically a very wide variety of body shapes. And as always, we've had many different global anthropometric databases, so you can accurately portray your target demographic. They're listed over here. And the mannequins also have a fully articulated spine, shoulder, and hand. They're kinematically accurate. with a physiological range of motion limits built into the model. So it doesn't allow you to like bend the wrist back too far or turn the neck too far. So it allows for very accurate ergonomic assessments. And also because we can represent so many different body shapes now, it makes our clearance and reachability studies a lot more accurate. And the realistic looking model makes the results that you need to communicate to others subject to less scrutiny. So we have the industry-leading breadth of human performance tools. These are our quantitative ergonomic assessment tools. You can see the tools themselves listed down here, and they cover strength capability, injury risk analysis, posture analysis, and fatigue. And we stay up to date with the latest methods. We've recently introduced the strain index here, and also the arm strength evaluation tool is a newer tool to us as well. So we're constantly putting in the latest research to make our human performance tools even more usable. So now I'm going to go through kind of 3 demonstrations on how to use our tools in these 3 areas. So in the area of doing a reachability study, a visibility study, and also safety. So this is, you can see this is the different looking mannequin. This was the previous generation of mannequin. And this is going to be a reach assessment. So we have the ability to change the gender of the individual. We have different options here. We can even put in a boot and glove figure. And then we can choose from all of these different anthropometric databases to properly represent your target population. So this is a US database, and we're going to look at putting in a 5th percentile female. So since this is a reach study, we'll look at the smaller end of the spectrum. So you can see the big size difference between, that's a 50th male, and this is a 5th percentile female. And we're going to see if she can reach this tool over here. Now, just by looking at the person relative to the data, you can see that's not ideal. But we can also use this tool to make recommendations, like if she does need a platform or a riser, how high does that riser need to be? So it can allow us to do a number of different what-if studies with the layout as well. So this is just a quick reach envelope. It's everything she can reach with the palm of the hands. And you can see it doesn't encompass the tool there. And not all jobs can be changed, so we may have to recommend that a certain size person do a job. This can help with staffing requirements as well. So we're going to quickly populate that same area with a 50th male. And you can see that it does, the reach envelope does encompass the tool, but it is kind of at the high end of the reach zone. So at this point, we would go a step further and actually posture the person in and see what that posture looked like as well. So we do have these kind of quick, easy posture prediction tools. It considers the weight of the object, if there are any bracing surfaces. So basically, in this case, all we have to do is kind of grab the right hand and tell it to grasp the side of that tool, and it will automatically calculate the posture. And it even curls the fingers around the object using collision detection algorithms. So if I adjust this grasp a little bit, you'll see it recurl the fingers around the object. So really just by looking at the posture here, in a second you'll see it from more of a side view. You can kind of tell this isn't ideal just from visually seeing the person in place in the posture. You see the elbow is a little bit ahead of the shoulder or above the shoulder. But if I want some quantitative data, I can turn on one of the analysis tools that looks at the overall posture and whether or not it's comfortable to the operator. So what I'm going to do is turn on the OWASP tool, You can see the back and the arm turning yellow. The highest number there is for the arms. And there's also a little bit of warning there in the back. So it's telling us it's not an ideal posture, especially if this is something he has to do over the course of the workday, as opposed to just a one-time task. So if I move him up, you can see that automatically corrected the posture. We're seeing no corrective actions necessary. And I can see how far I had to move him up. So we need to put a platform of at least 350 or so millimeters to make it acceptable, so we can provide that input into the person that's doing the layout. Okay, we can also look at visibility studies. So we're going to start out in that original configuration with the feet on the floor there. And we're going to direct the line of sight towards those hole locations that he's trying to fasten. And what you see there are vision envelopes. So those are the areas of the forward vision, the areas that would be the most visually acute. So you can see those holes are within that area, but what we don't know is how well he could kind of see up and into those holes. So for that, we can actually open this eye view window and see right through the mannequin's eyes. You can see if I turn the part, highlight the part there, it's very difficult to see the actual hole because he's a little underneath where he needs to be. So if I move him up to that optimized location, not only does it make the posture better, but now he can kind of see up and into those holes. So it's much less of a blind operation, and he can see what he needs to do. And next, we're going to look at safety. So here we're doing kind of an installation, a hose installation. And I'm just going to do a quick static study here. I'm going to provide some feedback into engineering or design on how much force he's capable of exerting. So I'm going to open the force solver tool here. And with that left hand in this current posture, we're going to make the force in the horizontal direction here. So he's going to be pushing it in. And I'm going to solve for how much force he can exert. And I'm going to make the percent capable so it's acceptable to 90% of the male population. You can see the limiting body element was the wrist, and he can handle about 9.1 kilograms of force. So if that force required is greater than what he's capable of, we may look at doing something like changing the posture. So I just raised him up a little bit so he was at a more optimal posture. The arm is in a much more neutral position here. So now I can resolve for that, and it'll go from 9.1 kilograms to 11.6 kilograms. So now he can handle the required force just by giving him better access to the parts. And next we're looking at, this is going to be an actual simulation. He's going to take this first wheel. The weight of that object is 8 kilograms, and anytime he is interacting with that object, it's going to assume that he's carrying that 8 kilograms. And then at the point in time where he has to push it onto the fixture, it requires 100 newtons of force. And the second part there, I think, was 10 kilograms, and again required 100 newtons of force to push it onto the fixture. So I'm going to activate different ergonomic reports here, and I'm going to display some notes, and then we're going to run detailed reports after that. So you can see some notes here. So as we run the simulation, you'll see these notes change. You see the body turn orange. That was the OS tool saying that he was in a bad posture. Now it's turning yellow. And as he goes back to pick up this other object, you may be able to see the low back tool flagging that he's beyond the NIOSH recommended limits for low back injury risk. So you can kind of get really quick updated information that way, and then we can activate some actual ergonomic reports to give us the real nuts and bolts of what's going on in this simulation. So it's looking at the posture that he is in for every frame of this animation, and the gender of the person, and also the loading conditions. So we're first going to look at the ergonomic metrics report here, and this tells us what percentage of time in that cycle he spent either standing, sitting, or walking. It tells us how many steps are in that cycle. It also tells us how much time is spent, or the percentage of the work time spent working overhead, lifting above or below what's considered waist height, when he's carrying an object, or working with both hands. So this could be useful for return to work initiatives. And then we also get a physical demands report down here, which tells us when we are in either a mild, moderate, or significant posture range. So you can see the wrist here. We're in a significant posture range for quite a bit of the cycle due to the fact that he has to kind of pick that part up off the pallet and then turn it 90 degrees to put it on the fixture. And you'll see a little bit of shoulder issues here too. There's some significant amount of time spent in shoulder issues as well. We can also look at, this kind of speaks more to efficiency. We can look at how many close, moderate, or far reaches there were. So if we're looking to maybe shave time off of that cycle, we can very quickly see that we didn't have any close or moderate reaches. They were all far reaches. We can also look at what tasks required the most hand travel distance. So in this case, it was going in and picking those parts up off of the pallet. That was the most hand travel distance. So reducing these can reduce some of the cycle time. And then the next report we're going to look at is the percent capable. So this looks at what percentage of, in this case, the male population will have enough strength to perform a certain task. And in this case, we start to go to 90 and a little bit over 90 when he's picking those two parts up off the pallet. So again, that's our problematic operation. It's taking the most time, and it's also the most demanding on the body. It's starting to cause issues with the hip or the back. So this would lead us to look at one of the low back tools. And here you can see that this is the compression forces at the L4 and the L5 vertebrae. And when they go above 3,400 newtons, that's where this yellow line is. It's starting to tell us that they're at a more high risk for low back injury. So again, this is where he's picking part 1 up off the pallet, and this is where he's picking part 2 up off the pallet. So it's putting him at risk for low back injury. And then we also have a tool that looks at the cumulative effects of loading. So it's looking at before that, we're going to look at the OWASP tool again. So not only can you do that in a static mode, but we can also look at it over the course of the simulation. And same as the other tools, it's definitely flagging the points in time where he's walking over and picking the parts up off the pallet. And then this final report allows you to put in a shift duration and the repetitions per shift. So it allows you to see what the cumulative effects of low back loading. So if he does this 200 times, it's telling us that it's red, so the compression exposure exceeded the recommended threshold value. And I can look at editing the repetitions. So if I change this to 150, you can see it starts to go green now because we've allowed enough rest time in the cycle to make this more acceptable. But what we would want to do is probably look at modifying that task to make it a little more acceptable for the operator. So this is when we can use these notes. They come in handy. I can start to kind of iterate it forward until the compression goes to an acceptable level. And now we can measure what the lift height is, or what the lift height should be. So we can provide some feedback on kind of a minimum lift height for those parts to reduce injury risk for the operator. Okay, and then usually I go through and show the female model as well. I can quickly switch over and kind of morph the simulation and the female model will run the same motions through as the male did. But for the sake of time, I'm going to kind of speed through that part and show the last report. Here's the timing report. So again, this shows the overall cycle time, which was 22.4 seconds. And it takes each task and breaks them up into a series of subtasks. So to get that first part, they had to walk a certain distance, and it automatically calculates that distance and assigns a time to it based on MTM1 codes. And then he had to turn, bend, and reach. And again, it automatically calculates the reach distances and assigns the duration, and then gives you an overall time for the task and then the cycle as well. So these types of studies can help determine your staffing requirements, improve quality. We can detect all these different types of assembly or layout issues early before everything is laid out on the shop floor. We can help to decrease time by reducing the number of blind operations or visibility issues, and of course ensure the safety of workers and reduce workman's comp claims, medical expenses, and improve productivity. And then this is my last slide here. What you saw in those three examples was kind of creating all of those simulations manually. We have a task-based simulation builder that allows, it's kind of a wizard-based approach to simulation. You'll say get object and he'll automatically walk over and put the hands on the object. So those were all created manually, but we can also connect to motion tracking hardware, and then the real person that's wearing the motion capture suit will actually drive the movements of the jack mannequin here. So we can really very rapidly do these what-if studies. We can very rapidly and accurately get human motions in either real time or we can play them back later and process simulate human for analysis. So that was my last slide. So back to you, Philip.
And with that, I will now turn things over to Allison to take us into the next segment, which is the use of digital models in manufacturing.